Then I'll introduce today's speakers. So today we have Yuan from MIT. You all know, I'm sure, so I'll sort of keep in the spirit of not belaboring introductions. He works with Pablo at MIT on twisted bilayer systems and correlated phases in systems, etc. So without further ado, Yuan, take it away.
Thank you, Cory, for the introduction. So, hi everyone. I'm Yuan from Pablo Javier Alios Group from MIT, and in this talk I will be talking about our recent findings in the phenomenology of competing orders, nematicity, and novel Joseph effects in the superconducting phase of mostly magic angle twisted bilayer graphene. So, from the excellent talks since yesterday, you probably already get an idea of how simply by twisting different 2D materials, a variety of new physics can arise from the simple underlying materials such as graphene. In particular, superlattices made from twisted 2D materials or stacked different 2D materials with different lattice constants has really become a new scheme for studying strongly correlated physics, and it closes the gap between studying the correlated physics in conventional materials such as qubits and in ultra-cold atoms through the optical lattice techniques. And since this topic has been introduced, from yesterday's talks, the introduction to these materials has been quite thorough. I'll just quickly go through the intro part and just jump directly into our newer data. So the band of twisted bilayer graphene comes from the hybridization of the Dirac cones in the mini Brillouin zone, as shown in this nice 3D picture in recently archived paper. I just copied it. When the twist angle is close to the 1.1 degrees, the central band in these spectrums becomes very flat, and this is known as the magic angle. So, at this magic angle, we have flattened bands, which means that there are isolated states in real space and separated by a length scale about 14 nanometers. And in our case, these electrons are localized at the A stacking sites, while at the AB and BA stacking sites, the empty, they are kind of empty. The electrons don't like to stay there. So in this flat band system, we have, about 2 years ago, we found, this correlated insular states, and in particular, if you dope this correlated insular state, you get superconductivity. The correlated insular state have an energy scale of a few to 10 Kelvin, and the superconductivity occurs up to 2 to 3 Kelvin. So since we have the actual knob of the twist angle, we can also map out the phase diagram in terms of the the twist angle. And since this is determined at the fabrication, we have to measure many samples to get these statistics. And from this map, we can indeed find sort of a dome in twist angle as well, and which point towards a maximum TC around 1.1 degrees, which is in agreement with where the flattest band is predicted to occur. Since our discovery of the superconductivity, there has been many other experiments on different Moire systems that also claim signature of the superconductivity near correlated insular states, which Andrea also mentioned yesterday. But the evidence of the superconductivity in all these systems, so far seems to be quite, subtle. They either don't show a true zero resistance, such as in, I think in the last case, and there are also, some cases the IV curve just doesn't look like what you expect in a real 2D superconductors, like for example in this kind of curves. So there has been paper recently also suggesting that, these observed data are actually can be attributed to some more trivial effects such as geoheating, not actual superconductivity. So one question is, in fact, it was also asked by one of the audience yesterday during Andrea's talk, how do we know that the superconductivity in twisted bilayer graphene is authentic? And people tell me just having zero resistance is not sufficient to show something is a superconductor. So indeed, typically, to legally claim a superconductor, you need at least 2 of these 3 criteria. So of course, one is zero resistance, and we already have that. And one of them is Meissner effect, the explanation of the magnetic field from a superconductor. And another one is phase coherence. But as I will show in a minute, in a 2D superconductor, the Meissner effect doesn't work by principle. So therefore, we at least want to show, if the third criteria, the phase coherence, is possible to be demonstrated in twisted biography. So that will be the first part of my talk. I'll show you, how we can measure the phase coherence effect in the superconducting phase of the match angle twisted biography. The simplest way to get phase coherent transport in a superconductor is to create a Josephson junction, which is two pieces of superconductors interrupted by another phase, either a insulator or metallic phase, but the superconductor can still flow through this junction. And Josephson junctions have a maximum critical current that you can pass through. And this critical current shows the oscillation when you apply a magnetic field through the junction, analogous to the Fraunhofer pattern in a optical single-slit diffraction experiment. But twisted biography is a 2D superconductor, as I said, and there is actually a fundamental difference in how it interacts with the magnetic field when you go from 3 dimensions to 2 dimensions. So in bulk 3-dimensional superconductors, the magnetic field induces a circulating current through the sample, trying to screen out the magnetic field. And this is what the microscopic mechanism behind the Meissner effect. And the magnetic field only enters the superconductor into a depth called the London penetration depth, which is denoted by delta. And the magnetic field decays exponentially within this boundary of the superconductor. Of course, the junction area, the magnetic field would penetrate, but it only still penetrates through this width of 2 lambda in this case. However, in the 2D limit, although the magnetic field will still induce a circulating current through around the edge of the sample, the magnetic field generated by these currents are negligibly small, and effectively the magnetic field will basically penetrate the entire superconductor almost uniformly. Now this can be seen from a more quantitative argument. The screening current in the magnetic field, you can work out this from the London equation. It is proportional to the thickness and inverse proportional to the square of the penetration depth. And these two quantities usually merge into this big lambda, which is called the Pearl length. And the magnetic field generated by this current that runs at the edge of the sample is basically proportional to this b times the width of the sample divided by the London penetration depth. So in like real 2D materials, the d is extremely small. So the London penetration depth can reach millimeter scale, which is much wider than the typical length scale of our sample W. So this means that the magnetic field generated by this screening current is going to be orders of magnitude smaller than the original magnetic field. And this is why Meissner effect basically just doesn't work in 2D in principle. So this would also have an impact on the Fraunhofer pattern one might expect from a 2D superconductor. And according to the Josephson relationship, the current in the Josephson junction is related to the phase difference across it. And for a wide junction, you need to integrate the critical current density, times this phase difference, integrate over the width of the sample. So, and basically, the oscillation periodicity in the magnetic field is determined by how fast the phase across the junction winds as a function of the distance into the junction. So for a bulk junction like here, the phase winding rate is basically determined by the 2 times the London penetration depth, because because the magnetic field only penetrates in a small strip of width 2 lambda near the junction. But on the other hand, in the 2D case, because the magnetic field kind of penetrates everywhere, this relationship doesn't really work anymore. And there is no simple formula that you can expect to calculate the phase winding rate. So you have to do some numerics, and the only length scale that matters here is basically the width of the sample. So there's some numerical factor, but this rate of the phase winding would now basically be determined by the length scale of the width of the sample. So you would expect to have a very different Fraunhofer oscillation periodicity in this case. So in order to see this experimentally, we basically, in our typical device, we will put a narrow top gate on top of it so that we can independently gate the middle region of this device. And, we can use this to achieve a Josephson junction, basically. So the transport in such device is quite complicated because there are multiple PN junctions when you have 3 gates. And basically the bottom gate controls the phase of the entire device, and which we can tune into the superconductor by putting the bottom gate voltage here. And you can see there are 0 resistance here. And then along this line, we can vary the top gate to try to gate the middle part into an insulator. And indeed, when we do this, we find there is a nice oscillation pattern of the critical current in a magnetic field. And this, qualitatively matches with what we expect from the previously mentioned Pearl physics. So yes, this basically just shows that, yeah, indeed the superconductivity in twisted by graphene is authentic, and there is a phase coherence. So this picture summarizes the phase diagram of TPG twisted by graphene, which you're probably already familiar with, and everything in this map occurs in this within this narrow pair of bands. So next, I want to talk about the anisotropic phase that we discovered kind of by accident in magic angle twisted by graphene, and this actually occurs both in the normal state and the superconducting phase. So I want to spend 1 second on the cuprates. In many cuprates, if you look closely at their phase diagrams, there is a kink on the underdoped side of their dome, which usually occurs around a doping fraction of 1/8. And in cuprates, this behavior is generally understood as a competition between the superconductivity and a charge ordered phase with broken symmetry. So, it'll be interesting to see where there is also such thing in twisted by graphene. And in one of these, sample with, around 1.09 degrees, and this device have a very high TC of above 2 Kelvin. In this sample, we indeed find this resistive feature on the underdoped side of the superconducting dome. And it creates a reduction, in a way somewhat similar to the cuprates that I just showed. Now, if this is only one sample, you might say, oh yeah, you have some inhomogeneity in the sample, so that you have just half filling shifted to here or something like that. But we think that's not the case because we see this repeatedly in, a different sample. Actually, now we have this seen in the third sample, and it seems to be only happening near this twist angle of about 1.09, 1.07. So we think this is something intrinsic to the sample. And we can see that the competing feature, this we call it like a wedge-like feature, it fully suppresses the superconductivity when we kind of assist it with a little bit of out of the magnetic field. And each curve you're seeing here is the TC at a particular out of plane field, and at about 0.09 Tesla, 90 millitesla, the superconductivity would be completely suppressed and it splits into 2 domes. So this phenomenon is also, somewhat reminiscent of the behavior in cuprates, except that in cuprates you have to apply a magnetic field of like 60 Tesla to see this effect. To study in detail about the symmetry breaking near this feature, we study the anisotropy of the superconducting state first by measuring its in-plane critical magnetic field. So a superconductor gets killed by a magnetic field, we all know that. And this magnetic field can either be in plane or out of plane. So for the in plane magnetic field, there is an extra degree of freedom, which is the angle in the plane, the rotational angle. Since twisted by graphene have a 6-fold symmetry, naively we would expect that it's basically it should be isotropic. But however, it turns out that the magic angle twisted by graphene shows a very strongly anisotropic critical field when we do this experiment, and suggesting that the system strongly breaks the C3 rotational symmetry inside the superconducting state. So it breaks down to a basically C2 symmetric ellipse. So we think that this kind of anisotropic behavior has something to do with electronic nematicity. And it turns out that many quantum materials show this kind of spontaneous breaking of symmetry both in the superconducting and normal state. And most notably, examples are iron pnictides, some series of cuprates, and also more recently the doped topological insulators. So nematicity refers to a spontaneously broken rotational symmetry breaks, basically, without a translational symmetry breaking. And starting from an anisotropic wave function, the electronic interactions, it could spontaneously lift certain rotational symmetry of the system and creates this kind of nematicity. Now to develop an electronic nematicity, one needs to have an ordering basically in the charge particle moment of the system. So in 2 dimensions, the quadrature moment have 2 fundamental modes, basically the dx square minus y square and the dxy. They are 45 degrees with each other. And in material with square lattices like cuprates and also some series of ironicides, these 2 fundamental modes, they transform according to different irreducible representations if you look at the group table. So this means that one can assume that they can assume different amplitudes and sign in their order parameters. And usually due to the computation between the different parameters, you only end up with one of them, which is either aligned to the lattice or is 45 degrees with it, which is called B1G and B2G respectively. And this thing is called IZ nematicity. It's analogous to you have to pick one of the directions. And it has been found in cuprates and ironicides indeed. But however, in twisted graphene, which is a triangular or hexagonal system, the situation is quite different. So naively, one would expect that the nematicity would just be locked to one of the 3 directions. But if you actually look at the group table of D6 group, for example, these 2 modes, they transform according to the same 2-dimensional irreducible representation E2, which means that the 2 order parameters, they are not independent quantities. They must be related by this kind of phase relationship, and this is called the XY nematicity. So that basically you have the two component order parameter which you have an amplitude and a particular direction, and this is called the nematic director. And this is something unique to the hexagonal system, of course. So all these systems, including bismuth selenide, some other ironicides, some heavy fermi, and of course TBG, they have this symmetry. So, but the bottom line is that in hexagonal systems, nematicity doesn't have to lock to any particular crystal axis, and in principle they can be directed to any axis. So here I'm showing our experimental data. So basically we measured the previously shown the anisotropic critical magnetic field as a function of doping and temperature at each of these points inside the phase diagram. So, and we can extract the axis of the nematicity at each of these plots. So we have a lot of data, and I cannot show you all the data today. But in general, you can see that firstly, at all these points, there is some degree of anisotropy, and the ratio is on the order of 1 to 2 or 1 to 3 along the minor and major axis of the nematicity. And also, what's important is that as a function of both the doping and the temperature, we see that this nematicity axis or director is indeed not locked to any particular direction, but it shows some rotation as you change doping or temperature. I'll just summarize the direction of this nematicity into this schematic plot. And we find that if we plot the nematicity director on this map, well, firstly, there is nematicity in the entire dome in this twisted graphene. And if we plot this director on top of this map, we find there are 2 distinct regions. So first, there is this slow rotation region where the nematicity is almost directly directed to a single direction, but there is some wiggling around that point. And then there is this fast rotation part of the phase diagram where the ellipse, it can rotate by more than 60 degrees. So again, we notice that there is something peculiar about this kink around TC. Yes, this fast rotation axis also happens around this kink. So we want to know a bit more about this, kinky feature on the TC, and especially in the normal state. So, in the normal state, the in-plane critical magnetic field cannot help us anymore, because in order to have a critical field, you first have to have superconductivity. So instead we try to measure the anisotropy in the resistivity tensor itself. So resistivity tensor is a two-component thing, but this is when the device direction is aligned with the like the principal axis of this anisotropy. So if you are along a general direction, you have to rotate this by this formula, and it's quite complicated. But the bottom line is that if you divide the rho xy part by the rho xx part, then you get something that is basically proportional to the anisotropy of the system, and times the sine of some angle. So as long as this angle is not accidentally 0 or 45 degrees or 90 degrees, then you this basically the ratio of the zero field rho xy divided by rho xx will give you information about the anisotropy of the system. But then before that, we have to fix some of something in the system to make sure that no like fake signal gets into our data, because in realistic samples the RXY probes are usually not perfectly aligned, so that even at zero field you might get some contribution from RXX into RXY, and this is known as the mixing of RXX. So there is a proportional factor here. So in order to correct for this, we basically take the RXX and RXY as a function of temperature, as shown here, and we kind of make the assumption that there is a geometric contribution to the RXY, which is independent of temperature. So at high temperature, we can calculate this ratio, and then we subtract this contribution twice, like from the RXX, and this is what we get. So indeed, at high temperature, we can do this subtraction pretty nicely, and then, but we see that at low temperatures, below about 6 Kelvin in this case, there is a large RXY signal, and this signal we attribute to the anisotropy of the normal state of the system. Okay, so now we can look at the, we did this for each gate voltage, and we can, plot this now in the color map. So we indeed see that above this superconducting dome, where the kink was, there is indeed a very strongly anisotropic region, and this feature is exactly at the same location as this wedge, and basically we find that this feature seems to be a different feature than the anisotropic superconductivity we identified like a moment ago. So we can compare it to the rho xx, and you can see quite clearly that this resistive feature in RXX corresponds quite nicely with the same location with the anisotropic feature. So we can also apply a small magnetic field, this zero field, and at 0.5 Tesla, we can see that the superconductivity is gone indeed, and this anisotropic feature, it turns insulated. But then the anisotropy itself, you can still see it's visible. But then like basically the idea here is that from this measurement in the 0.5 Tesla, you can see that while the superconductivity is definitely gone, the anisotropy itself is still there. So we think it's those two things are slightly the microscopic mechanism might be slightly different. By the way, this 0.5 Tesla data we obtained by taking the measurements in both 0.5 Tesla and minus 0.5 Tesla, and then anti-symmetrize, symmetrize in order to remove the contribution from the Hall signal. So we can conclude that in magic angle twisted by graphene, at least in a range of angle very close to 1.09 degrees, where the TC seems to be highest from our statistic of the TC, there is this phenomenology of competing orders, where the nematic superconductor, which happens in the entire TC dome, and the anisotropic feature above the TC looks like a wedge. They seems to be competing, and this competition creates a kink on the curve of the TC. And also in this competition region, the nematic director have a quick rotation as a function of the doping and temperature. So you may wonder what's the microscopic origin of this phenomena that we don't know. But recent STM in experiments suggest that near the Van Hoff singularity, there is indeed some tendency to form some charge ordering. So that could be one contribution. Then there is also other experiment that points towards the phase transitions when you are close to integer feeding factors like the 2 here. And this could also be one possibility of why there is this kind of anisotropy in the system.
Sorry, Yuan, just to let you know you have 5 minutes.
Yeah. Sorry.
Sorry. My buzzer was interfering. Yeah. You have five more minutes. Sorry.
I see. Sure.
Okay. Yeah. Sorry about that.
Yeah. So. Yeah. Great. So the last part I will talk about is our more recent experiments working on understanding the chemical potential and the compressibility of the magic angle twisted by graphene. So in this collaboration work with Shahal Ilani, we studied the local compressibility of twisted by graphene using scanning single electron transistor. It's made of carbon nanotube. And the compressibility in this measurement clearly shows that phase transition that occur at all integer filling of the superlattice. And these trends could be qualitatively explained by a model of spontaneously lifting of the spin and valley flavor, symmetry inside the system due to a enhanced Coulomb repulsion. So one thing worth noting is that even in the new X1 state, where typically there is not much transport features at low temperature and zero magnetic field, there is still these bumps in the local compressibility measurement, which means that whatever phase transition that would take place is actually already there, even at zero temperature and zero magnetic field. So inspired by this experiment, we directly measure the chemical potential of the magic angle twisted by graphene using a structure shown here, like on the left. So this is a technique first demonstrated by the Emmanuel Tudik group in UT Austin. And if you take 2 pieces of graphene and put them very close together, you can measure the transport on one layer to figure out the chemical potential on the other layer. So here we put one layer of the monolayer graphene on magic angle twisted by graphene, separated by a few nanometer barrier of HBN, and then we can use them to mutually sense the other layers' chemical potential. The conversion formula can work out. It can be worked out from the band alignment diagram here, and also the electrochemical equilibrium, which I'll not expand here. I'll just show you example of how this is done. So this column map shows the overlaid resistance of the orange one is the resistance in magic angle twisted by graphene, and purple is monolayer graphene. So if we track the orange feature here, which is actually the charge neutrality of the magic angle twisted by graphene as a function of top gate and back gate, you basically track the the chemical potential of the monolayer graphene as shown in the inset. And this chemical potential fits pretty nicely to your expectation from this formula, and you can extract the Fermi velocity to be about the right value. Now we can also turn on a small magnetic field, and then this spectrum of the monolayer graphene is quantized into number levels, and in this case the chemical potential measurement also agrees very well with what you expect from the textbook formula for graphene. So, of course, the more interesting part is how to do this for using the graphene to sense the twisted by graphene, as shown here. So, interesting, we find that at low temperatures, there is a range of density with negative slope of chemical potential versus density, and this is known as negative compressibility. The appearance of the negative compressibility is a clear evidence that the Coulomb interactions are playing a very important role here, because this is basically analogous to telling you I'm trying to fill water into a bottle, while only to find that the level of the water drops. So we can do this temperature at arbitrarily high temperatures, and as long as the graphene charge neutrality point is still visible in transport. So the negative compressibility itself disappears around 20 Kelvin, but the modulation in chemical potential, which signifies the phase transition physics, it persists up to 70 Kelvin. So we're trying to obtain now a more quantitative understanding on this, and the result would be posted quite soon. So with this temperature dependence, one can also try to extract the entropy of the system actually. So from the free energy, which is by definition is like this, we can work out the Maxwell relation, which relates the temperature derivative of the system to the density derivative of the entropy. And by integrating this, we can get the change of entropy inside the system. So I'm just showing a very preliminary data here, and we have more data on this, but I'm not going to show here today. But we're currently working with the Shahal group and the Arisberg group at Weizmann to get the complete understanding of this phenomenon and the implication of this. Yeah, that's what I'm going to talk about today, and thank Pablo and also Zhongming, which is a young student right now working with me, and also Shahal and also our theorist support, and also many MIT and Harvard people and also funding sources. And thank you very much.
All right, thanks, Yuan, for a really fantastic talk, and thanks for including a large amount of information right on time. So that's rather nice of you. So again, I'm going to address some of the text questions that were raised during the talk first, but please raise your hand and I'll get you in the order if you have additional questions. So the first came from Ivor Martin. He asked the following: presumably the simulations in Josephson effect assume that phase is fully ordered. How does KT physics, i.e. fluctuations, affect that analysis?
Yeah, so the simulation is done basically at 0 temperature, so we didn't consider that physics inside this picture. I guess.
I don't see Ivor. If you want to add to that, I'm happy to allow you to. But, oh, sorry. So I don't see Ivar raising his hand. So I'll go to the next question, which is from Oscar Vivek. His question was, is the low T activated transport at magnetic field equals 0? This had to do with the anisotropy measurements. Is the low T activated transport at 0 field in the correlated insulator also anisotropic?
Can I ask you to repeat?
I think the question is basically in the correlated insulator. If you look at that, the insulating state, do you also see anisotropy there?
So a normal state anisotropy, as I showed here, I think, for example, here, yeah, there is strong anisotropy here, but not like there, which is where the correlated insulator kind of occurs. So I think the answer is no, or negligibly small.
Oscar, I've allowed you to talk. If you want to add to that, you can unmute yourself. Okay. Okay, so next question, let's go to Chen-Ke Zhu.
Hello?
Yes.
Yeah, so you showed very quickly the curve of the compressibility you measured at different filling. Can you go back to that slide? Yeah, right. So at what temperature is this data taken?
This I don't remember. I believe it's somewhere. It should be 300 millikelvin.
Oh, so do you know at what temperature these bumps will disappear? I mean, this will be flat or?
So in their measurement, I think, in this a single electron transition measurement, I think it's around 30 Kelvin or so.
30 Kelvin. Okay.
Yeah. So this is definitely, this thing is like, we call it like the parent state of the system. Like it occurs to it persists definitely much higher temperature than the correlated insulator themselves.
Okay, thanks.
Okay, so next question actually is from the panelist. Eun-Ah, you have a question?
Yes. So the normal state and isotropic state where you see the suppression of TC, Yeah. When you made comparison with cuprates, where we see the origin of that in cuprates is not nematic, it's associated with charge density wave. It happens near a special commensurate filling, and one suspects there's charge density wave. Now, your observation of anisotropy is based on sigma xy or rho xy. So it just, I guess my question is, do you have a way or reason to rule out charge density wave there? It seems to be kind of local. Yeah.
Yeah. So okay. So maybe I was a bit loose on the term. So basically, when we say nematicity, we don't really know whether there is a translation of symmetry breaking. So it could be
right.
either that or
it could be charge density wave.
Yeah, it's
right?
I think called magnetic phase or something like that. So
either
of those could be possible. Yeah.
Right. Okay. Thank you.
Okay, next question comes from Bert Halperin. So Bert, unmute yourself and go ahead, please.
Yes, I was trying to understand what determines the orientation, if you know what determines the orientation of the nematic order, and whether it seems to be the same in more than one sample, or whether this was just measured in one sample.
Yeah, that's a very good question. So in terms of the normal state anisotropy, we don't have a way of really determining the angle, as you can see. We can, we can only tell whether there is an anisotropy or not. But this we have repeatedly observed in, many samples in the same range of two samples. I mean, not, three samples in the same, almost the same two samples. So the superconducting anisotropy, on the other hand, we see it basically in every sample. So regarding the question of what determines the angle of the anisotropy, I think it is basically a combination of the intrinsic nematicity and the some small strain inside the system. So we don't have basically if you thermocycle the system, the nematicity direction is always the same. So yeah, I think we actually have.
But in different samples, it can be different.
Yes, but also there is one question in. There is one, uncertainty in this system is that we can't really know what is the crystallographic axis of artificial graphene. So, comparing from sample to sample is kind of tricky.
Okay, I see. Okay.
Okay, thanks, Bert. So next question is Efrat Shimshoni.
Yeah, hi. I wanted to ask sort of along the lines of Ivar's question, whether you did any measurements to try and fit to Kosterlitz-Towles theory, like the temperature-dependent resistivity and maybe AC transport.
So we're trying to look for KITP phases only in the maybe simplest way. Just look at the IV curve and try to extract the KT temperature. We've done that level of analysis. Yeah. So maybe not the level that you're describing.
Okay.
Okay, next question is, sorry, Yuan Wang, if that's correct. I apologize.
Yeah. Yeah. So I just have a quick question about the compressibility, or some sort of confusion, actually. You showed in some ranges, the compressibility is actually negative, experimentally measured, right?
Yes.
But this is why I'm confused, because from thermodynamics, we know if a system has a negative compressibility, it means basically your theory is wrong. It's actually the grounds that you're using to obtain this negative compressibility is actually unstable toward a first order phase transition. So do you have any comments on that? Maybe I just missed some points, some subtleties. Thanks.
Yeah, I'm aware of that point. So I know that if you have negative compressibility, that you have some sort of instability inside the system. But I didn't know that it just means your theory is wrong. Is that what you're saying?
I think
I'm not saying your experiment is wrong.
Maybe the confusion is that this is not really the total compressibility of the system. It's kind of the compressibility as compared to if it were a metal. So the actual, there's not actually a negative capacitance when you see negative compressibility in 2D electron gases. So I think what experimentalists mean and what theorists mean might not be the same.
Okay. Yeah, this is what I was suspecting. Thanks.
Okay, thank you. Next question is Eddie Stern.
Hi. Could you show the entropy data again?
Yes.
The last slide. Right. So how much of a precision should we assign to the delta S? I mean, what would be the error bar if you had to put an error bar?
Yeah, that's a good question. So I let me say just conservatively, maybe 20%.
20%. Ah, so that's pretty precise. Okay, thanks.
Okay, looks like Bert, you have a second question. Is that right?
It was just a comment that for the definition of compressibility in a system with Coulomb interactions is that you subtract off the essentially infinite, relatively infinite part due to the Coulomb interaction, and so therefore it's a matter of definition. What's left can be negative.
Okay, thanks for the clarification.
Okay, so because we started about 5 minutes late, we still have time for 1 or 2 more questions. Sorry, it looks like Addie, you have another comment. Addie Stern, you have another comment?
I don't have another one.
Okay, sorry, I'm trying to lower hands also. It's a bit confusing, so I apologize. Okay, so I have a question maybe I'll ask then. So maybe I'll ask a question, which is, I was a little bit, I was curious about the sort of anisotropy measurement. And it looks to me like the region where you actually measure anisotropy is purely in the transition region of the superconducting transition. Is that correct? Or?
No, it actually goes quite above that. So, it's, goes up to actually probably visible even at 8 Kelvin. So,
in your sort of example curve of how you get the anisotropy of the subtraction. So here, for example, right? Yeah. So it looks like,
Yeah. So here I'm picking a point. Maybe it's strong. Like the amplitude is strongest, so it's around there. So it's like here.
I see. Okay, but it persists well above that. But it persists mostly above that in this sort of wedge region specifically.
Well, the other main thing is that even you kill the superconductivity, it's still very strongly here. So that's why we believe it's not directly related to the superconductivity.
If there's no other questions, I'm going to ask one more about the Josephson Junction data. So this was really kind of interesting, but it looked like the data was like sort of curious. Like there was like there's double peaks there. And I'm sort of just curious,
Oh, this?
Yeah.
Yeah, so, this kind of like inhomogeneous feature in the Fraunhofer pattern is quite, we see it quite commonly somehow. I think.
Do you know where that's coming from? Or?
It might be related to just some like weird current flowing path inside the junction. It's not fully uniform through the junction.
And this particular measurement, can you just say, was it acquired? What was the actual condition? So what was the N, SIS or SNS?
This is SIS. This is the point.
What were the filling fractions of each region?
So this S is just -2 minus delta, and I is the -4.
Okay. Okay, so I think we have time for one more question. If not, then we'll proceed. Ivar, did you want to make another comment? Sorry, I see that you added to the text. Yes, okay. Ivar, if you want to mute yourself, you can go.
Yes, okay, so is it working now?
Yes, yeah, sorry about that earlier. Yeah.
Okay, great. So yeah, question on this one. So alternative would be, I guess, to do like a vertical structure between the twisted bilayer graphene and something like aluminum. Is that something that would be feasible?
Yeah, in principle, I guess. But the only thing is, if you put a metal directly on there, you can't gate it anymore.
Right. Right. I see. I mean, you could use metal, I guess, as the gates, right? As one of the gates. So say if you put your twisted bilayer graphene, then some spacer, insulator, and something like aluminum on top.
Yeah, that's definitely possible.
And then you could, by applying the in-plane field, you could again look for Fraunhofer patterns.
So the suggestion, I guess, is like generic superconductor insulating barrier graphene superconductor, right?
Well, then basically, that barrier would act both as a gate and a tunneling barrier, right?
Right.
So,
I mean, we need separate tunneling barrier.
I guess it's in principle possible.
The structure is possible. I think I'm going to close the discussion here, but I've already. Okay, so thanks everybody. So I think we'll move on to Lauren. Thanks, Yuan, for a great talk, and everybody else for a great discussion.